when you're ready there, read about the hot air balloon, and we'll see if we can sketch that out. All right, now don't panic. I don't expect you to be at the point that you're like able to do this completely independently. There's still some things you need to hear. But I think you'll find that as these things start to take shape, I want you to start to find that you're catching on. Okay, try to be in a thinking mode, not just completely listening to me. Did anybody ever take a hot air balloon ride? You did?
My dad did.
All right. So is this like a normal, like a weekend?
It's a hobby.
Okay.
It's not as I've been up 45 times.
Whoa, 45. That would, from my experience, be the record for people. Where do you guys fly?
Jim Max Ice Cream River, right there.
And then you probably mainly blow east. You blow towards the river?
Yeah, we go towards the river. We go over the river, and sometimes we come back towards New York, depending on which way the winds are going.
Any exciting stories, like favorite memory, crash landing?
We went over the river before, and we actually touched down into the river, and our feet got soaked. It was actually it was fun, but
Was that on purpose?
yeah, my dad just wanted to like see what he tried to like coast right over the river, but he didn't go up fast enough, so landed right on top of the river. Got a little wet.
All right. Some people are like, no, thank you. I don't want nothing to do with that. Well, my grandfather took us up on a hot air balloon. He was one of those guys that he lived to be like 95, but he still felt like he was 60. He just kept going. And one of his bucket lists was go on a hot air balloon ride. So I remember, though, my parents kind of like signing our life away. I was like, you sure you want to do this? Because there's all these things you have to sign. But we took off near Dillsburg and floated around up that way around Pinchot and such. So it was fun. I was probably too young to kind of know, to get too nervous about it. You know how you don't know as much. All right, so what do we have here? It's a good problem. It's a classic problem that's going to help you guys see a triangle. It's not going to ruin the fun for you to realize that it's like a triangle problem. So balloon. I'm sure you can do a better drawing than that. I guess I could too. That looks a little better. So we got a balloon, and it is above the ground. And again, it's a classic triangle problem. Right triangle to be exact. So go ahead and sketch that. It'll help you to see where we can put in some of these numbers. And that's where I want you to start to, again, get kind of active and involved. What's the first number we see? 500 feet. Okay, now we have to understand that is 500 feet on the ground. I guess as I read it, I'm trying to figure out how can a student know that. I think we would know that because there's a rangefinder. Now, if you're a little bit like, what's a rangefinder? It's just something that can measure an angle. And that's exactly what's happening right here. We'll make the rangefinder a point on the ground to keep it simple, but it's able to measure this angle to be pi over 4. Sorry, it's a little weird. It's pi over 4, not p over 4. Okay, now, I guess even as I'm looking at it, I'm kind of like, okay, there's no other givens here, I don't think. But let me add a little bit more to this sketch, which will help you guys in future problems. And that is to think about this dimension as x, kind of self-explanatory, but that would allow us to think about this dimension, which you'll find out gets closer to the unknown. We can think about that as y. But we pretty much have what's given to us. We have what's given. Let's kind of move into interpreting, this is, oh, I forgot to put my magic pencil up here. Let's go into interpreting. This is kind of like step 2, the calculus information. Now again, step 2, step 1, honestly, all the first 3 steps, they kind of blend together. But as far as interpreting, that's where we want to start thinking about rates. Now there is a number in here that says something radians per minute. I know it's kind of weird, it's in radians, but a radian is just an angle. So we get this idea that something is changing at a rate of, as it says, 0.14 radians per minute. Now I left out something in the numerator. I don't know if you're going to want to leave it out, but I want you to think about what is changing. It's the change in something over the change in time. Okay, we kind of said it. It's the change in radians. That's an angle. It's the change in theta, d theta dt. And as you guys get to the point where you're like, I'm getting this, you're going to let those kinds of statements sort of roll off your tongue. It's the radian rate. It's the angle rate. Now, it might be helpful to realize that this pi over 4 is not a rate. It's just a static value. So maybe we can label that and make that a little more descriptive. We'll call that theta equals pi over 4. And then we get into step 3, which again, kind of all blends together, just trying to organize what's going on. But it's important that you identify what you're trying to find. You know, just like a good old word problem, what are you trying to find? So we read the last sentence carefully. How fast is the balloon rising? How fast is the balloon rising? Now, we're not going to write down how fast is the balloon rising, but we need to go over here and we need to realize that that has something to do with this dimension. But it's not y, but it's the change in y. It's the dy dt. And when you write dy dt, that stands for the rate that y is changing. It's basically how fast the balloon is rising. What do you think? This is kind of the given. It's kind of organizing it. It's basically organizing all the information. Do you feel like there's something else that we're missing? Okay, there's not, but you know, we can just talk about it if you want to. We need to come up with an equation. Step 4 is to use an equation. Maybe another way to say it is to come up with an equation. Now, when you do this, it's not just like you get lucky or you ask the teacher. You have to look at this problem and you have to think about the variables that are being related. I see x's and y's and thetas. We need an equation that would relate x's and y's and thetas in a right triangle. Okay, now sometimes somebody will call out Pythagorean theorem, you know, like maybe like x squared plus y squared equals, I guess, z squared if you want to use that. Okay, it's not right because it doesn't relate theta. It doesn't involve theta, but it is on the right track because it's a right triangle formula. Right triangle formula that uses x's and y's and theta. Do you hear something? If you had me last year, you sort of have the secret ears. If you didn't have me last year, like, what is that guy doing? Can you please explain what I'm doing?
SOHCAHTOA.
Okay, good. SOHCAHTOA drum. Now, Aaron, I knew you heard the drum first. So what equation relates x, y, and theta? So we would say that the tangent of theta equals. Now, that's important because sometimes people are like, I know it's tangent, but like, how do I say it? Like that. You just write the formula. What I'm getting at is you don't need to plug numbers in, okay? Just one step at a time. You just come up with the formula. Now, what we have to realize is that we're going to do the derivative of this formula. But I don't have this as a step. But before we do the derivative, remember how I said this on Friday? Is there anything that gets plugged in pre-derivative? What that means is, there any numbers up here that are constant? You see, x is never going to change. In other words, dx dt is equal to 0. I don't want to go there. I don't want to get a derivative, a dx dt of 0. So I'm going to plug 500 in. I'm going to plug 500 in pre-derivative. Listen, you always do that. You always plug in constant values. Now be careful. Don't plug in pi over 4. I'm serious. Don't plug in pi over 4 just because it's in my diagram. You have to understand that pi over 4 is not constant. It's changing. If my hot air balloon's going up, then this angle is changing. Differentiate. I'm having trouble with the middle of that word. Differentiate. Yep, it's calculus time. I mean, it's all been calculus, but we need to do the derivative of this equation. Let me give you a little help here. I don't want to do the derivative of a fraction either. So, one more kind of pre-step, I guess maybe I better do it down here, is to just multiply 500 over to the other side. I mean, it's supposed to look more natural because now 500 is a coefficient. And I hope we know how to do the derivative with a coefficient. Well, let's do the derivative of both sides. The derivative of y, not dy dx, but dy dt. So the derivative of y is dy dt. Now, the derivative of 500 tangent is the derivative of a coefficient. And now we get into the good stuff. The derivative of the function, the derivative of tangent. The derivative of tangent is still secant squared. Now watch carefully here. When you rattled that rule off to me, the derivative of tangent is secant squared, you meant with the inside left alone. So I'm going to leave the inside alone. But then we have to do the derivative of the inside. The derivative of the inside, this is important, is d theta dt. You get that rate. You get that rate. Now take a look. Okay, we were trying to find the change in y over the change in time. We were trying to find how fast this was going to go up. That's good. That's in my formula. I've been given a theta. That's good. And then I think I've been given a change in theta. What I'm pointing out here is that there's nothing in this formula that I don't know. If there was, then I have the wrong formula or the wrong derivative. So, plug into your derivative. Plug into your derivative. Okay, now be careful. You know how to do that math. Instead of just me writing it down, let me do one quick model here because it's a little fancy to type in there. Secant is the same as the reciprocal of cosine. Secant squared is cosine squared. Now, if I put the square right there, I'm not squaring pi over 4. Don't worry, I'm going to be squaring the cosine. That is the 1 over cosine. If you want to be super sure, you can add an extra set of parentheses, but they're not needed. Okay. Oh, make sure your calculator's in radians. It's a textbook problem. It was kind of made to come out as a whole number. I mean, that doesn't mean it's right, but just saying it really does work out But do you realize what 140 represents? Okay, 140. It really is the change in the height. So it would be feet. I think this thing's in feet, right? And then per time, it was in minutes. So the hot air balloon's going up 140 feet per minute. We're getting a little closer. We're getting a little closer to the point that we want you to start to get this. So to help you do that, there's another problem. It's number 3. Start by reading it. And let me say that I hope you're not scared to try to start to sketch it, to try to start to set it up. That's how you're going to learn. Now, don't be scared to look up here. I'm not going to give it all away, but the whole like north, south, east, west intersection, it's supposed to be one of these. Yes, another right triangle. Some things that you should be able to fill in could be an X and a Y. What I'm really wondering is how you doing with the rates? How you doing with the, 20 miles an hour? How about the 60 miles an hour? And do you feel like that there should be something else in this sketch? Let me guide you a little bit. There should be. This time that distance, that diagonal distance, is actually needs to be part of this problem. Label it as Z. Does anybody think they know where we can or how we can label 60? I'm sort of skipping to the 60 miles an hour. It's in the last sentence. Can you like get a little calculus-y with me? How would you label 60? It's all right if I'm not going to put somebody on the spot. Do you feel like it involves the letter Y? You're warm. Don't be scared. Take the plunge. Say it. Let it be dy dt. You do have to just say these. You have to create these. It's the change in y. Now, that's pretty good if you were thinking that. There is one small thing. I even missed it. I remember the first time I looked at this. Because the object is moving down when it comes to movements from an origin. This is like the origin right here, this point. So because I'm moving down, because my distance is getting smaller, Do you know what I'm headed at here? This has to be negative. It's a little tricky, but again, because the distance is getting smaller, the rate has to be negative. How about 20? How about 20? Good. Now here you have to realize that the distance is expanding. I think it says that. It says, yeah, the distance between the two cars is increasing. So this diagonal distance is starting to spread out, meaning that this is positive. Have you gotten to this point? Have you identified what you're trying to find? Okay, it would be the change in x. It would be dx dt. Dx dt. Okay, now that's kind of steps 1, 2, and 3. And like I said the first day, I don't really care if you label them. We didn't even label the steps. We just kind of blended it all together. We tried to set the problem up, interpret the numbers. It's equation time. Now, these equations, like I said, don't just come out of thin air. It's an equation that relates these variables. As I look at this problem, I see x's, y's, and z's, and dx's, dy's, and dz's. You have to look a little bit into the future. The dx, the dy, and the dz will come from the derivative. But we need a formula that relates these variables. Okay, well, this time it is the infamous Pythagorean theorem. It is the Pythagorean theorem. Are there any numbers on the board that are constant? Is the length of y always going to be 0.6? Is the length of x? Are these going to be constant? Do I need to plug something in now? Okay, the answer is no. So it's time to do the derivative. Now watch, this is, it's not the first time we did this, but that is doing the derivative with an exponent. But it is the first time that we've done a derivative with like so many variables. But it's really no big deal, as long as you understand that each one of these variables is like a little chain rule. So the derivative of x squared is 2x to the first power times the derivative of the inside, dx dt. And then we'll do another little chain rule. The derivative of 2y is 2y dy dt. See how we end up getting the rates. They pop out of each of these derivatives. 2z dz dt. Okay, now we're trying to find dx dt. That's good. That's part of the formula. As you look over the rest of the formula, there should be a place for everything and everything in its place. But maybe those that are a little quicker, you realize that this z has not been identified yet. Okay, but it's only a Pythagorean theorem away. This problem has a little extra step where I have to calculate something based on the given. And again, just look at this through a simple geometry, algebra lens. You can find z. You can find z. Make sure you understand this is not calculus. I'm not plugging it into the derivative. I'm actually going back, and I'm just doing a good old side squared plus side squared equals hypotenuse squared. Okay, and you're going to find out if you're punching those in your calculator that this was intended also to work out sort of evenly, so to speak. It comes out nicely to be the number 1. z equals 1. I would like you to understand that to say z equals 1 means that these two cars are 1 mile apart. I don't know. I mean, I know it's kind of like, really? They're a whole mile apart, but from here to here is a distance of 1. Okay? In other words, it's a distance. Just like each one of these distances. 0.8 is an x distance. Of course, dx dt is what we're trying to find. 0.6 is a y distance. But the change in the distance was negative 60. And then we found 1 to be our z distance, but 20 is our change in z. I know you guys can do that algebra, but it's interesting if you just step back here that this is how you relate these three variables. Okay? It's not like it's just a basic relationship. It's a derivative, and it's a derivative that involves three variables. But you can be confident that the derivative you created up here is going to relate all these numbers. Very interesting. And honestly, the answer that you get is realistic. Let me make sure I show it. Multiply these together, get 1.6. What do we have here? Is this, what is that number? Comes out to be negative 72. Okay, so we get negative 72 here. Is that right? Yeah, that's right. Okay, so that has no variables. It's just a nice little negative 72. And then over here we have 40. So yeah, if you're going to solve that equation, and kind of what I wanted to point out is that the negative not only makes sense here because you're going down, but it makes sense here so that it allows me to add 72 to both sides. Get yourself, 112. And once you get 112, you can divide that by this coefficient. So I wanted to point out that the negatives actually make sense when they start getting plugged into these equations. And you guys will see some other problems like that, maybe sooner than later. But now if you solve that, you will end up with 70 miles an hour. Which, by the way, is not negative, as in terms of physics, we're actually going further away from the starting point. Since it's increasing, then that value should be positive 70. All right, and so like we said, it looks like the bad guy is going to get away. Or maybe it's a bad girl. It doesn't always have to be a bad guy.